Hey, you there?
Hello.
Hey, how you doing?
I'm good. How are you?
Pretty good, pretty good. Um, I didn't notice every time I'm in here and it's like, oh, it's a little after 7, like 30 seconds after 7. I say, did I get the right meeting? Because that second time, and now
Oh
I'm
yeah.
almost paranoid now. Are you just clicking on the link in the email? Is that how you get here?
Yeah.
Okay, makes sense. I've been like triple checking every time. So anyways, did you want to send anything or did you want to go over what we've done already? Or I didn't see any. Oh, there it is right there, of course. Okay, also I wanted to ask you if there was anything like I could do to make it make the lesson better. If there's anything on your mind, if maybe I need to go slower, maybe I need to go faster, probably not that, but I was thinking sometimes I go a little too in depth and maybe it's not particularly useful, some of it, just because it, the class seems a little simplified, at least compared to like a calculus-based course. Do you know what I mean? But yeah,
Yeah.
is there anything that you would want me to do or that I'm not doing?
I think it's actually really good. Like I understand everything, and I think you go in depth like just enough.
Okay, good, good, because I don't want to, I mean, I love it obviously, and it's exciting to me, but I don't want to waste your time either, because it's about getting
Yeah.
a test and good grade, and you know. Okay, good. That's great. Thank you for the positive feedback. And please let me know at any point. This is your time. You know what I mean? So,
Okay.
okay. So yeah, let's look at that first guy there. Looks like we have, let me see real quick. Oh, there it is. And you have this stuff in front of you, so it's okay that I don't bring it on screen. Um,
Yeah,
this
it's right in
format
front of
is
me.
working for you. Okay, cool. All right, we got a monkey. Monkey's hanging out. They could have just had like, why does he have to shoot a projectile that kills him? Why don't they just shoot a little, here's an apple, monkey, All right,
Yeah.
anyways, we got this guy here. So this is projectile motion. It sounds like this is a new thing, maybe a new topic, maybe not.
Yeah, it's just like one last unit before our final.
Oh, okay, okay. So it is a final that's coming up that he keeps pushing. He has no idea when it is. So, okay, good to know. Okay, so we got fires a crossbow horizontally on a monkey tree. Great. The monkey steps off the branch as the hunter fires. Does the arrow hit the monkey? Okay, so this is like a qualitative. Okay, so not too much math really, but we want to understand what's happening here. And
Hmm.
it's important to know, or it's important to take everything literally. So that's how I'm going to approach it. Um, I'll show you what I mean. So let's draw what we got here. Pictures, as you know by now, hopefully are always important. We got a guy who's standing there, or girl, or whatever, everything in between, right? And a tree, monkey. Let's just make it very simple. Looks like they are okay. So they are at the same height. Let's do different color for monkey. I guess you got it in front of you, so you know that's the monkey. Okay, so first thing you look at this, you see, what are the objects? When we're talking about Newton's laws, we're talking about projectile motion. When we're talking about physics, we have to identify the particle, right? And so there are
Hmm.
two things happening here. This is the first object. It's I want to make sure to be very clear since the first time we're covering it, at least you and I. And it may be obvious, but I hope it's obvious. But there's a crossbow. That's the first thing, and it's moving, right? So that's why it's kind of obvious. He fires this thing, and we can, like, when you look at this, you want to think about it, and you say, "Oh, trajectory. What's going to happen when this crossbow fires?" We're looking at a piece of paper, not a video, and so you can use your intuition, and you know that when you throw something, well, it's going to go whatever direction you throw it, and eventually hit the ground, right? So, crossbow. This is what we think the crossbow is going to do, right? And
Hmm.
maybe even something like that. I guess it would hit the tree at this point if it did that. But again, this is qualitative. We're not given any numbers. So I can't tell you exactly how far it goes or when it hits the ground, but I know for a fact that it's
Hmm.
going to do this. It's going to look like this somehow. And we know here that the monkey drops down. So you can use yellow and I'll use a solid line.
Wait, are
This,
you sharing your screen?
oh, I'm not. I have it set up and okay, sorry about that. That's a good, you don't seem like that kind of person to yell at me, but you yell at me right away and say, hey, idiot, share your screen. Okay, cool, great. Let me see. I don't want to do too much. Okay, was that clear, right? I mean, I was setting it up. The important part that the key things that I just said was that you identify the objects that you're using equations for, and that's what's moving, right? And it's the crossbow and the monkey in this case. Two separate objects,
Mhm.
and so there's like two sets of equations. Oh, two separate objects are moving, so there's two laws. We apply two sets of equations, two laws of physics, kind of, right? And so, like I said, this is the trajectory of this crossbow here. This is all qualitative because they're not giving us any numbers. And so I know, like I said, you're gonna throw something, and everybody knows, a 5-year-old knows, right? You throw something and it goes the direction you throw it, and it's gonna hit the ground eventually. That's what I was doing here. So that's the trajectory of this crossbow.
Mhm.
Okay, so that happens, and then the monkey falls, he goes straight down. That's his trajectory. Okay, so that's what happens, and they want to know, does the crossbow hit the monkey? Now you have to say, okay, they don't give us anything, but I do know something. This is called free fall. When the monkey's going,
Mhm.
this part is free fall, monkey is free fall, and crossbow is projectile motion. Um, Kind of the same thing. It's actually just the only difference. It actually is the same thing. The only difference is that it is 2-dimensional, and this is 1-dimensional. But I'll tell you that one of these dimensions is that. So that's very crucial to understanding projectile motion. Because if you can understand projectile motion, well, you definitely understand that, guaranteed, because projectile motion is free fall plus this horizontal motion. We'll get into that a little bit, maybe in this one, but maybe in another one as well. So what happens in free fall? Do you know?
Um, it okay, so in this case, the monkey's in free fall, so it would go down at a constant acceleration.
You got it. That's exactly right. And what is the value? We actually know that value of acceleration that you just said. Do you know? Do you know what it is?
Um, 9.8.
Yeah, we call it little g, whatever, baby g, whatever you want to remember it. And it's units of acceleration, just like from weight, right? Weight equals mg. That's the same g. Why? Because we're on Earth. That's the only reason. It's the gravitational acceleration of Earth. And so you got it. That monkey, it falls. It just drops off the branch, meaning that it has an initial velocity of 0. I don't know if you've gotten into this part about defining these variables, but he's not moving. And then all of a sudden he jumps off. So imagine, just hold your hand out and drop a ball. That's literally it's the same exact thing. Monkey has different mass, but I'm starting from rest, and then it just falls, and Earth's gravity takes over.
Mhm.
And so you got to think that, or you got to know that this is projectile motion. And so this part here, this free fall is actually happening here, but it's just in a parabolic trajectory. A parabola from math, right? X squared, y equals x squared.
Okay.
Of course, it's just
Mhm.
upside down in this case. So you say, oh, if you want to get real mathy, which you probably don't, it's minus x squared, right? An upside down parabola.
Mhm.
Great. That's literally the motion in projectile motion. I don't know how much in depth. We have to answer the question, obviously. Does it hit the monkey? And my intuition is to say no, just because it has to cover this distance. Do you know the answer? Did he give the answer?
No, we were gonna go over on Thursday, but I just wanted to make sure I understood it before we went over it.
Of course, I want to make sure that we get the right answer here. But all of this is definitely useful for understanding projectile motion. Right, as the hunter fires. That makes sense. Okay, so I got a little carried away here, but hopefully that was useful because this is all this stuff is true, of course. But the reason is that it does hit the monkey if you aim directly at the monkey. That's the point here. That horizontally at the monkey. If he aims it just a little bit above, it'll go above him. And if he aims it a little bit below, it will do it, and it will go below him. And so if you aim it straight at him like he is, it will definitely hit this guy. So crossbow, I'm not even going to draw the heights or anything, just draw the true projectiles that are moving. So this is the motion you want to remember. Monkey goes straight down. Let's do that.
Mhm.
And then projectile motion. And so I don't need any numbers or anything to know that it is going to hit the monkey if I shoot him right at. And the reason is because both of these things experience the same gravity. 9.8 meters per second.
Okay.
Even though this is a parabolic trajectory, you have to remember that gravity is always, always, always straight down. And so I don't care about this horizontal motion is the point here. This thing can be broken up into a vector like that. And that's what projectile motion is. I'm not sure how much you'll get into that, but this component here is gravity, but there's no acceleration in that direction. What do you need?
Mhm.
What do you need to have acceleration?
Gravity.
A force.
Oh
Newton's
yeah.
second law, right?
Mhm.
You have to have a net force, non-zero net force, of course, to have acceleration. And there is no force in this horizontal direction. So it's just a constant trajectory in the horizontal. And then this acceleration downwards, the same acceleration as this monkey or any object in free fall. But the point is when you combine them, right, that's the combination of motion and projectile motion that gives you that parabolic trajectory. When you throw something,
Mhm.
whatever, I don't care what you're throwing and how far you're throwing it, it's always the same. Okay. Do you have any questions on that one? It was maybe a little too much, but hopefully I got the main point across, which is on this page that I'm showing you right now.
I'm just a little confused. So wait, what is the final answer for this?
If you shoot it, if you're firing directly at the monkey, it will. It does
Okay.
hit the monkey. And the reason is because of this. They have the same exact downward gravitational acceleration.
Oh, okay.
Anything else on this one?
I don't think so. It makes sense.
Okay. Okay. Person traveling at constant velocity and high speed train throws a ball straight up in the air. Where does the ball come back down? What path does the ball follow? Okay, so I gotta remind myself here, keep it simple. And so it looks like maybe this thing is going to the left. That's usually these arrows indicate velocity, so we can say that. Great. Train, Poison, and then a ball. Great. So if he throws it straight up, this person throws it straight up, it's going to come directly down. It's going to go
Mhm.
straight up, and then it's going to come literally right back down. Where does the ball come back down? Right back into their hand, literally into their hand, and it follows that straight up and down path.
Okay.
And the reason is because these things have the same velocity. I noticed you wrote behind curve slant. Are you saying that he told you that this is the leftmost curve?
He kind of just had us make predictions on what would happen.
Okay,
So that was
I
my
see.
guess.
Yeah. And so there's nothing else really going on here. And so if you're moving at the same velocity then you're going to, nothing's going to happen. It's like if you were standing on, if they were standing outside of the train on the ground. I mean, you can imagine it, or just do it yourself. Go outside or stand in your room or your living room and then throw the ball up. Well, you know what's going to happen, right? I mean, it's not going to go any crazy way. If you throw it straight up, obviously, it's going to come back to your hand. It's going to go straight. And think about it.
Mm-hmm.
You're not moving at all. You're just standing there. But now picture yourself moving in a train. Um, and you're moving with some velocity. Whatever the train is moving, I don't care. They're fast, right? So they're going pretty fast. It doesn't matter. But you are stationary. Your velocity relative to the train is zero. That's what's important. And most importantly is that the ball and you have the same velocity. So and again, um, no curve motion occurs. I guess you can say it just straight up and down. So think about, apply Newton's first law here, right? We're moving at constant velocity. What does that tell you? What does Newton's law tell you? There's no change in its motion.
Mm-hmm.
If there's no net force, which there's not here because it's constant velocity, which means acceleration is zero, no net force, there's no change. Now, I don't know if you go into the second part, but you can follow, if the train is moving forward, accelerating forward, all of a sudden there's an acceleration. Well, now you got some net forces and the ball will go backwards this time. And you
If
can,
the train accelerates forward.
yeah, if the train accelerates forward, because the train is accelerating, but the ball still has that constant velocity. Does that make sense?
Oh,
It's,
okay.
if it's in the air, it's not touching the train. You're accelerating because your feet are on the ground, but the ball's in the air, and now it's moving at constant velocity. This is always, I was always into physics, but like this is a great. You think about when you're in the car, right, and you turn. Everybody has felt this. What happens if you turn left? Your body goes to the right, right?
Mm-hmm.
And so, literally, the problem we're talking about is why that is. Because, so say you're going down the road 40 miles an hour. You're not speeding because you're smart, right? And so you're going down here, and then all of a sudden, so what's happening when you're going down the road straight at 40 miles an hour? The car's moving 40, but so are you. You're moving straight along the road 40 miles an hour.
Mm-hmm.
Say the road, and this is your car, and you're moving down there. And let's say now you turn, there's a turn up here. Well, now your car has to turn, obviously, or you're going to go off the road. So your car turns, but guess what? Your body is still going that direction. And so to make up for it, your body does what that ball does right here when the train accelerates, because your body is not accelerating or turning at the same rate that your car is. And so you're still going straight forward. Why? Because of Newton's second law. You haven't hit anything. You're sitting in your chair, fine, but like that seatbelt or the door that you hit when you turn, that's what stops you from going straight. But your motion is
Mm-hmm.
still going the same direction.
Okay.
Think about that next to your car. It's really simple and powerful, and um, I don't know. It changed my perspective a little bit. It's like, oh wow, it's very simple, but it's pretty cool. There actually is a use to this, all this stuff. Okay, I'm getting the second one. I gotta rotate these guys real quick. Okay, a rock is dropped. Okay, you see that? That's what I was talking about. They throw the rock. Oh yeah, here you go. They drop it. One of them, just like that monkey, it's the same thing. I don't care what it is or what it's doing. It's free fall. It's going straight down. The
Mm-hmm.
only the only thing that's acting on this ball in when it's dropped, right? You see those two arrows or those two line segments, I guess you might say. This one,
Mm-hmm.
this one is the monkey from before. Now it's just a rock. I don't care what it is. It's still literally everything we talked about. Free fall. Only thing that acts is little g, 9.8 meters per second squared. This thing now is in place of our crossbow. Again, I don't care what the object is or how far it goes or what. It's qualitatively all the same. We call this projectile motion. And notice this upside down parabola. It's pretty close, and you don't draw it perfectly, but it's an upside down parabola, the motion there. So rocked and thrown in horizontally at the exact same time. Which rock gets to the ground first? So if you understand the monkey problem, you understand this one. The only thing acting, the only force or acceleration or whatever, well, sorry, it's the only force, the only acceleration, that's exactly what it is g, straight down. What's the direction? Straight down. What's the direction when it's dropped horizontally? Straight down. Let me get a better one. Boom, straight down. What's the acceleration on this projectile motion here? There's no horizontal acceleration. There's no acceleration in this direction. Why? Because only gravity acts, and gravity always points straight down. So you can think about every moment through this thing. I don't want to draw red there. Every moment is g throughout its trajectory. I don't care what direction it's moving. It would be moving that direction, right, along its trajectory.
Mhm.
So these rocks hit the ground at the same time. Why? Because they have the same acceleration.
Okay.
So the thing to remember, if you look at this one, not sure what to do, or you look at the monkey problem, not sure what to do, look at both of these at the same time. Okay. Anything with that one?
I don't think so. It makes sense.
Okay, cool. Going a little much here with the acceleration throughout here, but if you do get it, it'll give you a deep understanding if you really can take home this message. Okay, same type of thing. Bomb is dropped from an airplane, and they're violent. Continues to travel straight ahead at a constant velocity. Fine, where does the bomb land? Okay, so this is okay. When you said the backward slant or the behind the plane, are you thinking about air resistance?
Yeah.
Because I mean, you're 100% right, right? I mean, I'm kind of breaking my own rules here. It didn't say ignore air resistance before, right? I mean, with the okay, you're 100% right if you have air resistance, and if we go back, I'm looking at that one, and then if I look at the first one, I mean, if you have air resistance on the train, yes, it will be a backward slant, but notice that air resistance is a force, and most importantly, they need to say that in this problem, and I'd be really surprised if you had to account for air resistance, because it's really complicated. I mean, engineers get degrees in that to understand the effects of rockets and footballs and space travel, right? Because you'll kill
Mhm.
people if you don't understand that, right? I mean, you better know
Yeah.
exactly what the air resistance and the drag is at every single moment where that rocket's going up. But it makes it really complicated, and it's really hard to understand. So I hope, in fact, if you it sounds like you don't have like a great relationship with him, like, you know what I mean, like go up to him after class and say, hey, I didn't understand this, can you explain it a little bit, um I'm not sure, maybe you do, but if you do go up to him and say, are we ignoring air resistance or not, he'll be like, oh, you're right, and maybe he should be impressed, at least if he's actually cares about what he's teaching. So you're right, it goes backwards, and I honestly, if you have air resistance, I couldn't tell you if it was a backward slant or that curve. It depends on how strong the air resistance is, right?
Uh-huh.
So what I'm going to do is just assume that there's no air resistance, because that's what everybody does in the beginning. That's what you even do in a calculus based course. So try to remember that. Um, are we ignoring air resistance or not? Because it's really important. It changes the motion. Because why? Because you have extra forces acting on it. Now it's not just gravity acting. Now there's an extra drag force, friction force. You covered that a little bit. Remember, it always goes against gravity, against the velocity. So it'd be that way for air resistance. So I'm like I said, we're gonna ignore it this time. And for the plane, imagine you got your plane. It's moving at constant velocity, no air resistance. Very important. So what happens in free fall when there is no air resistance? What is the acceleration is what I'm asking.
9.8
Yeah, which direction?
down.
Yeah, straight down always. I just wrote this for a little coordinate axes. Usually say positive is up, so that means gravity is down, and you would give it a negative value usually. But g is always straight down. You're right. So there's an acceleration, but there's also this component of velocity that is constant, right?
Hmm.
So imagine your crossbow. It's going to follow this trajectory is the point,
Hmm.
because it's the same exact problem as throwing a rock. I don't care what it is. This plane is giving it an initial velocity horizontally. Go back to that first one. That guy, that shooter is shooting that crossbow. He's giving it an initial velocity, right?
Hmm.
Same thing with the rock. It doesn't matter what it is. I'm throwing this thing, which means I'm giving it an initial velocity. And that's what these are key words here, right? The bomb is dropped, continues to travel straight ahead at a constant velocity. Some V naught. Now I do hope that I know everything I'm saying is right, but I hope that I'm giving you what you need. So make sure, there is no air resistance. Again, I'd be really surprised if there was, but this guy seems kind of weird. So is there anything about that that you need to talk about, or you want me to clarify?
Um, I don't think so. It makes more sense when you don't think about air resistance.
Yeah. Okay. That then you understand it. You definitely understand it then, because I mean, if you're taking, like I said, if you're taking an air resistance, yeah, it would be backwards, and you just confirmed that. Yeah, that's good. You're thinking about it the right way. Um, that's the first step to understanding the stuff. And now I'm looking at the next picture here, and we start getting into this vector stuff and a little more mathy, maybe with more numbers, which is always the harder part. I still got to let me download it real quick, and then okay. So we're going to look at new problems here, but don't forget everything. Like, it sounds like you have some understanding, and don't lose that, because I don't care what it is or what problem or what you're throwing or who's throwing it. It's the same. Okay. And it can, I mean, that's how people get screwed up by this. They forget these basic things, and that, oh, gravity is always straight down. Oh, that's right. Now it makes sense. I mean, I ran into the same issues when I was learning this stuff. So observations of a kicked football. Okay. What do you notice? Parabola, right? Is it what else? What else can you tell me about this motion here? I'm looking at the kicked football one.
Um, I don't know. It's going. I don't
That's
know.
no, that's fine. Anything you were about to say, it's going to the right, maybe, and that sounds obvious and maybe stupid, but it's not. Like, that's a small piece of this that you need to understand. Yeah, it's moving to the right, and I mean, we'll call this a positive x direction. You know, okay, great. What about gravity or acceleration? What is acting on this thing?
Um,
Remember, the motion is parabolic for projectile motion here.
Mm-hmm.
And so at every single point here, gravity is straight down. That's the acceleration. And then what the little arrows you're seeing here, this is the trajectory of the football at every single instant in time. Now, count the pictures. How many? 7. There's 7 pictures. And so I have 7 groups of arrows, but I could have an infinite number of groups of arrows because at every single point in time, you know, I don't know if go to the football games or basketball or any kind of sports or anything, but you probably know what a ball does. I mean, they all do the same thing. You throw them up and they come back down, but they'll just, if you throw it straight up, it'll come back down. But here we're throwing it at some angle. That's what we're saying here. Some angle, we'll give it a number, theta, right? I'm just saying it's a variable. I don't care what the angle is. And it's going to do this. That's what happens. And so these arrows are denoting the components of the vector.
Mm-hmm.
And it is for its velocity, looks like. So velocity is a vector, and we can break up any, let me explode this. So here's our football, and it hasn't done anything yet, but I kicked it. Great. And now I can break this thing up. We call it V with an arrow. It might be too much, but that's just what we call it. And this can be broken up into 2 components. In fact, let me make sure I'm doing the same thing as the picture. And we usually call it Vx because that's the component of velocity in the x direction and the component of velocity in the y direction. Now, I'm almost certain this is too much, unless you guys get into it, but probably not if you got your final coming up. But the point is that those, if you notice that there's only vertical arrows for each one, at the top of the motion,
Mm-hmm.
there's no vertical arrow, right? It's only horizontal. And then you have those horizontal arrows. I'm just looking at the first guy here. I should have pulled it up, but the first football picture on the very left, when it's still on the ground, there's 3 arrows, right?
Mm-hmm.
And one is completely
Yeah.
vertical and one is completely horizontal. So is that clear? Kind of what I'm trying to describe.
Kind of.
Is it the V and the VX? Is that throwing you off, or is it
Yeah.
just okay? Okay, so yeah, that's good to know. Let me stay away from that. So that's when it's on the ground, like we said, and I've just drawn the same picture here, and these are, this is velocity or the speed, kind of that shows you the trajectory, right? If I have a velocity, some velocity path, well, the object is going to move along that path, right?
Mm-hmm.
And so you see how it's pointing to at an angle relative to this thing here. And so, well, we know that there's also acceleration happening straight down. That's why there's curved motion.
Oh, okay.
So you have some initial velocity, and I guess I'll just saying the same thing, but it sounds like you had maybe an aha moment here. But it's curved because of gravity pulling it down, but it still has to go through its motions, right? It's not just
Mm-hmm.
automatically all of a sudden straight down. No, it takes time for gravity to work. So
Okay.
yeah, I guess I was kind of looking at that second picture too, because if you look at that second one there, I mean, compare those 2 pictures, right? The football and the cannon projectile motion and the independence of the x and y axes. Like, again, it's the same exact thing where now you're on a hill, right? But I've just changed my origin or where I'm firing the object.
Okay.
Because before I was kicking a football into the air. Okay, great. As soon as I let go of that football, it's going to follow this motion. Now take a look at the cannon. I didn't shoot it up this time. It looks like they're shooting it straight out. But now
Hmm.
compare that Canon picture to this, only the half of that football graph. Ignore this entire part and only look at this second half of the football graph where the velocity starts directly to the right. Well, hey,
Hmm.
it's the exact same.
Oh, okay.
And so, yeah, that's why that vertical motion only. Um, and this is why the crossbow hits the monkey, because if you look at that thing that says, that arrow there that says vertical motion only, what these crazy lines are indicating is that as time passes, when I drop something, when I drop something, see how it's
Hmm.
getting the successive time frames? These are all at the same time. T equals 0, T equals 1, where I've drawn
Hmm.
this. It's the same exact motion vertically if I throw it.
Oh, okay.
The motion is the same vertically when I throw it. And it's important because if you don't understand exactly what's going on, you'll say, well, what are you talking about? The motion's not the same. I have a parabola. I'm going over here. I've got this distance between them, and it's a parabola. I've thrown something rather than just dropped it. How could it be the same? Well, that's not what I'm saying. I'm saying when you break it up into what I was trying to describe before with this vector stuff, velocity broken up into
Hmm.
components, and all I'm trying to say is exactly what those words say: the independence of the x and y axes. You can treat, what that means is that you can treat this motion separately. You can ignore the horizontal motion when you do these problems and just focus on the vertical, and then ignore the vertical and go to the horizontal, but then you combine them in the end usually.
Okay.
Gravity free path, that's good to see too, the horizontal motion. So it's not going down. I'm looking at the horizontal path that says gravity free path. Of course it's not going
Hmm.
down. It just said ignore gravity. And we know that when we have projectile motion, the only thing that acts, the only force, the only acceleration, whatever you want to think about it as, try to think of it as an acceleration, but it gives rise to a force because of Newton's second law. It's always gravity pointing straight down
Hmm.
at every single moment here. Even though the velocity, as you see, if you go up to that football picture again, yeah, the velocity, the total velocity, it's always along the trajectory of the path. But that's if you understand the difference between velocity and acceleration. Okay, let me go to the next page here. A lot of qualitative stuff. I should have looked because we do want to. Okay, here you go. There's some math right now. Good. Okay. Are you comfortable with free fall? You want to cover that page on free fall?
Um, yeah, maybe just like a few problems.
Okay, sure. We got a free fall. And please, please do not get confused when you go from free fall to projectile motion because it's the same. There's just one component here, and part of it is free fall. Cliff diver steps off the 30-meter tall cliff. Um, I'm very glad to see you doing that. That's exactly what you want to do. I'll try to go through it. Stop me if it's too quick. I have, looks like you're using D or H. That's fine. I'll use H. It doesn't matter. That's what it's given. Great. How long will be in the air before they hit the water? So just as you said, time is a question mark. We don't know. But that's why A is written down also, right? We have acceleration. Notice the minus sign.
Hmm.
If you draw a picture, well, cliff diver steps. This is the classic projectile motion problem. You'll probably do this every time. Notice they did not leap off like that, right? If you've seen those, I think TikToks and Instagram, I'm probably on both, honestly, but they jump off and then they throw the camera off too, and it's cool. No, I'm just going
Mhm.
straight down, jumping right off. So that's why you can use this equation. So again, you ask yourself, okay, we've extracted the information, always the first step, extract, and we call it, I changed it to D just because that's what's on your paper when you do the equation. Then a picture sometimes. This is really when it's really useful. When you do constant acceleration problems, when you go through these steps and then identify for the equation. And of course, well, what equation relates all of these things? And of course, it's A equals 2D over T squared. You might have that on your sheet, hopefully, and then plug in the numbers, right? Well, solve for T, sorry. Are you comfortable getting this? Are you comfortable going from here to here? What would it be? 2D over A square root.
Yes.
Cool. And then, of course, plug in the numbers. Um, yeah. So honestly, this was just a extract, draw your picture, and figure out the equation, which I'm telling you, it's always that. Really figuring out which equation. Now, number two, they're asking how fast will they be going when they hit the water, right? Well, now it's
Mhm.
a different equation. Um, I don't know if I probably haven't. This one I wrote down before, delta V over delta T. That is what you're using there. A equals parentheses VF minus VI parentheses over T. It is the same thing, but it's just what acceleration is. So it's also this for Newton's second law, but then now you're using this for projectile motion, well, free fall and projectile motion, because remember, they're the same. So I don't want to get too confusing. So we write down exactly what you have. And again, acceleration is always the same. So you can always write that down as a given. I'm not sure if you did these like with the class or you did these on your own, but it looks like you've written down A equals 9.8 or minus 9.8 every time, which is great. You
Mhm.
always write that down when you're dealing with free fall. Okay.
Okay.
Do you know why the minus sign is there? Or are you okay with the minus sign?
Yeah, it's because you're like falling down.
Yeah, we have defined that down is negative because up is
Mhm.
positive. That's the only reason. I hope he doesn't get too much into it, but sometimes, down is positive, but it literally just depends on you. But keep it negative to make your life more simple, and hope he doesn't flip it on you. And one other thing about number two here is that we've plugged in the value of T. Now that's a given, right? That's why we say T equals 2.47 and all those numbers seconds, because we just found that. And so you're going to have to do that a lot in these ones. Finding one piece of information, time, and then, oh, now they want the velocity here. So you're going to usually have to find two things, just so you know. And then, of course, we got 30 meters. It's the same as before, minus 9.8. Now we're given time, and we find this equation. Oh, what's the equation that relates what? A, VF, VI, D, and T. Well, we don't need D, so but that's okay. It's still good to write down. You can cross it off, Oh, this equation relates A, VF, VI, and T. That's the one I should use, right?
Mhm.
Yeah, that's the idea behind that whole, I call it the epic problem solving strategy because I'm clever. And then last would be calculate, which just means put in the number. So I know I went fast through that one. I'm looking at number three here. Forgets to open the parachute. That's called garbage information, by the way. Nothing that's not useful at all. A person forgets to open their parachute. Well, okay, that means ignore air resistance. That's what that means. It's still considered garbage information though. But that's kind of what I was
Okay.
saying before. They usually tell you that. But again, yeah. So I know, like I said, I went through kind of fast on the free fall. I was trying to get to projectile motion also, but anything any issues on this page? Um, Anything you need clarification on?
Um, I don't think so.
You're okay, and you're good on number three also.
Can we do one similar to number three?
Yes, definitely. Okay, jumps out of a hovering helicopter. So let's just say you drop something, because that's what they're telling you. I don't care what it is. I don't care if it's a human, if it's a bomb, if it's a crossbow, if it's a monkey. It's always the same. So let's say hits the ground after they jumped. How high above the ground was the helicopter? So this one is just using different values. Again, okay, so the ball, I drop a ball. This is the same problem. I know it may not seem like it, but hopefully after a few times of doing this, you'll see I don't care what the object is or what it's doing. Just plug in the numbers. I'm going to drop a ball off the top of a roof, right? We'll call this building 50 meters. Nope, not going to do that, because that's what they want you to solve for. Okay, it takes some amount of time for it to fall. Makes sense, right? So let's say 10 seconds. Go on your
Okay.
roof. If you know, if you can get there, drop a ball and then have a stopwatch, and you'll see, oh, well, that didn't take very long. It took 3 seconds or whatever. And that's not hard to understand, hopefully. So I drop the ball and it drops 10 seconds. That's all they give you actually right here, which is like, okay, what, okay, all right, let's do our extract, right? Well, time is 10 seconds. What else do I have? Oh, right, I can write down acceleration, right? And it's always this for free fall. So, oh, that's good. But I still don't have an equation that relates these things, right?
Mm-hmm.
I guess technically you do if you're asking for the distance, and they're asking for the distance here. But what my point of going through this thing is saying that you have one other piece that they're not going to give you that makes it hard if you're not used to it. And that's the initial velocity. It's zero. And that's because, and you wrote that down here, VI equals zero. And that's what that means. They jump out and they're starting from rest, basically. Even though they're jumping out,
Mm-hmm.
the insinuation is that the initial velocity is zero. And so these two pieces are really important, because they're not going to ever give you them. It's definitely not on the test, and maybe only on the basic homework. But this is stuff that you need to read the problem and extract. And so again, you ask yourself, what? I need an equation that relates all of these things. So you go in your equation sheet, and then you say, oh, I don't need one of these. It's going to be that one, because there's an equation that says, oh, A is 2D over time squared. I have this, I have that, and I need that. 2 is a number, I don't care about it, right? It could be 10 or a million, doesn't matter.
Mm-hmm.
And when you have, that's part of that identify also, that identify step. What equation do I need? And then solve for the variable, of course. So are you comfortable with what I've done so far?
Yes.
Okay, that's good. I'm glad to hear that. And then, I mean, it is essentially solved. And then hopefully it sounds like you're getting better at doing the manipulations. You can solve for D, right? And then obviously plug it in. Let's do it real quick, actually, since we want to make sure we get the same answer and all that. So what would D, why don't you tell me what is D equal to? In variable
Um,
form.
it's t squared times a over 2.
Got it. Now that's perfect. And then we plug in the numbers. Now notice, maybe this is what threw you off before, there's an absolute value sign on A. And so
Mm-hmm.
do it without the absolute value sign, and hopefully you understand why there's an absolute value sign. So I'll do it with you. It's 100 divided by 2, right? T squared divided by 2 is 100 divided by 2, 50 times minus 9.8. And we get a distance of minus 490. But that doesn't make any sense. And one of the ways we know that is because we drew a picture. And you go back to your picture and you say, does this make sense? Does this answer make sense? And you say, no, of course not. If it was minus 490, then the cliff would be into the ground based on what we've done. That's why the absolute value sign is there. All it means is take away the minus sign, right?
Mm-hmm.
You're good with absolute value and what it means and all that.
Yes.
Okay, good, cool.
Yeah.
So yeah, that's why that's there, because we need a positive distance, right? That's what absolute value does for you. It says take whatever it is from 0 and make it positive. If it's negative, make it positive. So that's why, because we need a positive distance. And just one last thing to say here, if you can understand these three guys here, these three problems, then you're doing well on free fall, and probably have what you need. And if you understand this, then you already understand half of projectile motion. Okay.
Oh, okay.
Yeah. And then, like I said, this is the vertical part of projectile motion. Then we got to work on the horizontal part. But it's the same equations and everything's the same, except the acceleration isn't minus 9.8. So we'll get into
Hmm.
that next time, I guess.
Okay.
All right. Any last things to say?
I don't think so. I think I understand everything.
Okay, good. I'm very happy to hear that. Please, if you need anything to say, interrupt me, and for clarification, I don't mind at all. So,
Okay.
all right, I'll talk to you next time. Thanks.
Okay. Thank you.
Bye.
Bye.